Hello, this is the Singapore thread of Federated Marine Spatial Data Infrastructure Pilot 2023, supported by Wuhan University. This video shows the support solution provided. In the thread, the ongoing escalation of global climate change presents a significant challenge for Singapore, a coastal city-state surrounded by the sea on all sides. Greenhouse gas emissions are causing global warming and sea level rise at an accelerated pace. Frequent extreme weather events, such as hurricanes and storms, further intensify the risk of coastal erosion. To address these challenges, we will integrate terrestrial data from SLA and marine data from MPA, eliminating discrepancies between them. We have also developed a demonstrator for analyzing sea level rise data, building predictive models, and visualizing potential coastal inundation scenarios. Our research focuses specifically on a coastal area in the southeast of Singapore, as depicted in the figure below. In the integration of bathymetry data with terrestrial data, we first transform the pixel values to ensure compatibility. Then, we carefully identify the overlapping areas and proceed to resample them for consistent resolution. After that, we align the bathymetry data with the reference plane of the terrestrial data. Finally, we generate a final image output that effectively showcases the fused results of both datasets. To tackle the intricate challenges posed by various data sources, we leverage GeoCube technology developed by the Wuhan University. This technology enables us to expand DataCube by incorporating data from various sources, both vectors and raster data, with the goal of seamlessly integrating 3D and 4D data. Our data organization model revolves around 4 key dimensions: product, space, time, and variable. The product dimension provides a comprehensive view of product attributes, while the spatial dimension employs rule-based grids for precise location information. In the temporal dimension, we manage time series data, including data acquisition time and standards. Lastly, the variable dimension focuses on raster data granularity, describing attributes like rainfall, temperature, and wind speed within RS imagery. Here is our solution architecture, which will be divided into 3 modules. The data collection module manages various geospatial data resources. These raw data are processed into analysis-ready ARD data, structured into common geospatial formats. Next, the data storage module efficiently organizes analysis-ready data into a common multi-source isomerized cube, managing essential operations like reprojection, resampling, and data slicing. This cube is subsequently stored in various GIS databases. The data service module supports data centers and publishing resources via standardized OGC APIs, such as coverage for raster data and feature for vector data, promoting easy access and sharing of geospatial data and analysis services. Now come to our demonstrator instructions. We've gathered spatial and non-spatial data based on historical events in Singapore and even conducted simulations. All these functions are in the History mode module. Just click it to choose your next actions. In the default map, we've integrated land elevation, 3D building, and ocean bathymetry data from SLA and MPA. You can get a clearer view of this data integration by enabling the Render Elevation Ramp option in the top left corner. After clicking the Singapore Cube function, the right panel displays parameters and status. These settings align with the GeoCube design, and data has been processed and stored accordingly. In the product dimension, you can select your preferred product, such as Global ERA5 or the higher precision Singapore Meteorological Station data. In the variable dimension, you can choose the variable to view, like total precipitation. The extent dimension can use default global settings, ensuring coverage of your study area, with a recommendation of selecting extent level between 10 and 13 for the smaller study area. The time dimension spans from April 1st to April 30th, 2021, including a storm surge event in Singapore, which can be narrowed down to April 10th. Simply click Submit, and the results will be visualized on the base map. Lastly, the last slider controls time, allowing you to view specific time results, and the second to last slider helps you select tiles for visualization if focusing on specific areas. When you click on the wind field function, the system will display a visual representation of the simulated wind field over the Singapore area on the base map. After clicking Flood Analysis, opens a right side panel with operating options. Pressing Play button initiates an animated simulation portraying rising sea levels, depicting coastal inundation, and continuous inland erosion. In summary, in this project we used OGC standard APIs like coverages and features. Unfortunately, the integration of marine and terrestrial data has so far only focused on limited regions. Therefore, our future efforts will be centered on incorporating a broader range of marine and terrestrial data. Additionally, we currently use simulated and imprecise meteorological data solely for sea level rise simulations. In the future, we intend to incorporate historical or predictive data into our work. However, our demonstrator vividly showcases the impact of varying sea level rise heights on coastal areas.